All right, this is the last video in our sequence on Bayesian inference. So remember, what have we done so far? We talked about the Bayesian inference setup where we formulate some model of like, here's how there's something I'm interested in, and here's how that relates to the data I observe. Maybe we talked about multiple different things we're interested in with graphical models and understanding what is the relationship between all the variables involved. So we formulated a model, and we said that what we want is we want to compute the posterior distribution, which is like, what is the thing that we believe? What is the distribution of these hidden variables, the things I want to know, conditioned on my data? So like, if I know my data, how does that change what I know about the hidden state of the world? And we talked about, well, we can't always compute that posterior exactly. And we talked about rejection sampling as one way of potentially like approximating it using samples. And in this sequence, we're going to talk about using a different way, which is called Markov chain Monte Carlo. Specifically, we're going to talk about two methods. One is Gibbs sampling, and the other is Metropolis Hastings, that look at, okay, if I have one sample and I know that sample is good, instead of like throwing that sample away and starting all over, can I use that sample to like get me to the next one? And maybe like use that sample to like get me to the next one. And so saying, if your sample is kind of good, can you use that to like generate more samples from your samples? A little meta, but we'll see a little more concretely what exactly that means. So to refresh our memory on the math of it all, we have this setup where we have some theta that represents the unknown state of the world, and you have x that represents data you observe. And sometimes we've seen theta and x, and sometimes we've seen other variables used for those things, right? But it's important conceptually to think about what is the data I'm observing, and what is the thing I want to know? What is the theta? What is the like random state of the world that I actually care about, right? In the example with COVID prediction, we were really interested in the secondary attack rate, right? Like, what is the probability of somebody infecting somebody else with COVID? And that's something we don't know, right? We observe the counts, and we want to know reason about this hidden variable. So it's really important to think about what is your unknown state of the world and what is the data you observe. And then we talked about wanting this thing called the posterior, which is our distribution, or like we use the word belief about theta after observing the data. And we use Bayes' rule, and like we can grind through the computation. And what it boils down to is it's basically specified in terms of two terms. One is the likelihood, which is our distribution for x given the data. And the other is our prior. And remember, if we have a more complicated graphical model, then the likelihood may have like the likelihood of some data given like some parameters. The prior may be like some parameters and other parameters. And so this is sort of the simplified version. And then we have this thing in the denominator, which is like p of x, which we don't know, right? Like we specify a likelihood, which tells us if you knew the parameter, here's what the data would look like. And you specify the prior is like, well, before I see any data, here's what I think the distribution for that unknown thing is. And we specify those, but we don't specify the distribution over the data, right? So the way we get that is to say, well, I don't know what p of x is. So let me think about the joint distribution of x and theta, integrate theta out. But unfortunately, that integral, or that sum, if theta is discrete, ends up being intractable if theta is high dimensional, right? Like imagine you have like 100 different parameters. In the example you saw in the lab, you looked at 12 studies. What if we had 100 studies, right? Computing that integral over like 100 different dimensions is often intractable. So sometimes you can use conjugacy, where we know our posterior has the same form as the prior, but in a lot of models, you don't even get that. And so what we want is we want to find a way to do approximate inference. And rejection sampling was one way of doing that. In this video, we're going to talk through why computing the posterior is hard and show an example where even in a relatively simple model, trying to find a posterior exactly gets really intractable really fast. So remember the example of modeling heights that we talked about a little while ago, where we have every person, we have a label Z that indicates their gender, which is, in this case, we're modeling as binary. And we have, for each of the two groups, we have a mean, right? We have a mean that represents what is the average height for people in that group. So we have our group labels, which are these Z's, and we have our group level means. And in some cases, we might also model the variances differently for each group. But for now, let's just simplify. Say every data point is associated with a label and a mean, right? And we talked about this example for heights, but you can imagine you can model any kind of data this way, right? Any data where you imagine there's like different groups and the observations are normal, you can have this kind of a model. So the things I've highlighted are our priors, right? So we have mu k, where mu0 and mu1, where each one of these is normally distributed, and this is the group level mean, right? This is the average height for men, or the average height for women. And this is our prior distribution. This is what we think it is before we observe any data. And then we have Zi, which are our group membership. And we place a Bernoulli probability on that, right? Let's say it's pi0 is the probability that each of these observations is going to fall into group 1 versus group 0. Then we also have our likelihood model, which is the thing that I'm highlighting now, right? This is given a particular Z, right? Like this is what is the distribution of xi, the actual data point that we observe? Well, this says that x sub 7 depends only on z7 and both the mu's. And so the distribution for it is normal with mean corresponding to the mu for that group and variance corresponding to some variance sigma x. And we'll say that that's constant for all the groups just to make our lives easier, right? So we have some random variables, the z's, the mu's, and the x's. And we have some fixed parameters. The fixed parameters here are this overall mean of the prior, the overall variance of the prior, this sort of like probability of being in group 1, and this sort of variance in our observations. Right, so we have these fixed parameters, and we have this random model, and we have the graphical model drawn over here. Remember that observed nodes are shaded, so we observe the x's, and the z's and the mu's are what we're trying to infer. And why do we care about inferring the mu's and the z's? That's the whole point of setting this up, right? We want to understand what is the distribution of heights within each particular group, right? Within each particular gender. And you can imagine setting up other models where you want to understand what is the average behavior of data points from each group. And you also want to know the group labels, right? I want to know, does this person belong to group A or group B, right? In the height and gender example, that's sort of silly because you probably know it. But in many other cases, you also are interested in estimating the group labels. Okay, so this is we did this example with the heights, but this idea of having some labels and then depending on which group you're in, having a different mean, this is a very common pattern, and it's called the Gaussian mixture model. So this is how things are set up, and we want to compute, what we want is we observe the data, and we want to compute P of all the hidden variables, mu 0, mu 1, and z1 through zn, given the x's, right? We observe the x's and we want to know, well, what's the distribution over the mu's and the z's? And so we're going to use, our usual Bayes rule set up to compute this. And this is equal to, this is equal to the prior over our hidden variables. And the prior is this and this, right? We have a bunch of hidden variables here. So this is like P of mu0, prior for mu1, prior for z1 through zn. And I'm actually going to write this out and say, because I equals 1 to n, P of z sub I, right? So this is the prior over the z's. Before we observe any data, they're all independent. Great. And then the next part is the likelihood, right? We wrote our prior, now we write our likelihood, which is probability of, actually, let's leave a little room. This is, again, we assume that given the hidden variables, the data are all conditionally independent, right? If I knew what z's and mu's were, then the data points are independent. So I'm just going to multiply them together in the likelihood. And this is P of xi given zi, mu0 and mu1. right? And the forms of these distributions are what they are up there. I'm not going to plug in. I'm just going to kind of simplify this. And then over here, and the denominator is p x1 through xn, right? So I don't know how to compute that thing in the denominator, like just as it is, right? I don't know how to, I don't have a formula. I don't have a distribution for px1 through xn, but it sort of falls out of the things I already have, right? The things I've highlighted in yellow above. And in particular, I'm gonna write out, we can take the stuff in the numerator, and which is the joint distribution of the x's and the hidden variables, and we can just sum out all of the z's and integrate out all of the mu's. So this is equal to integral over all values of mu0, integral over all values of mu1, sum over all values of z1, sum over all values of z2, and so on, sum over all values of zn, times this whole thing up here, right? This is how we typically write it out. Remember, if we, it's just, if it's x and theta, then your denominator becomes integral, in the simple case of x and theta, p of x equals integral over theta, p of x given theta, p of theta, p of theta, right? Except here, theta is not just one random variable, it's like all the mu's and all the z's. So we have to do all of this summation, and like there's a d mu0, d mu1, because we're integrating. And now let's think about how, like, the actual mechanics of doing this sum and integral. Because we saw for like some simple 1D cases that you can approximate the integral numerically. You can call this thing at the denominator a constant. Great, maybe you can approximate that constant with a number. But let's think about how we'd have to go about doing it. Well, in order to do this, we'd need to sum over every possible combination of all the z's, right? This is a sum over z1, and then within that, we have to sum over every possible value of z2, and so on. So how many different combinations of the z's are there? Well, if there's n data points, then there's 2 to the n different combinations, right? There's like, if you have n data points and each one has 2 possibilities, then there's 2 to the n different combinations. Let's see if we can do any tricks with the sums to see if anything simplifies, kind of like we saw in our conditional independence example. So this is the integral over mu0, integral over mu1, sum over z1, sum over all the z's actually, of p mu0, p mu1, product over I, p z sub I. And since these two terms are both products, we can actually just group them together. P of xi given zi, mu0, and mu1. So notice that this last term here in the equation I wrote, this last term, which I'm highlighting, this is a term that involves x, z, mu, and 0. And if we think about what it is, it's really the same as it's this thing up here, right? Or specifically this, right? It's a normal distribution with mean, mu sub z, and variance sigma squared. So this involves we have to figure out z's and pick the right z, pick the right group, and then the mean for that group. So this is a really complicated thing that's not just going to factor as a simple thing we can just simplify. So then now there are no tricks that we can play. Sure, it's like we can pull these terms can be outside the sum since they don't depend on the z's, but after that we're stuck. We have to do this summation over this term, and that summation gets very intractable very fast. And so this is why we need to do approximate inference, because sure, we can compute our distribution up to a constant of proportionality, right? If I, this thing that I'm highlighting in gray, this here is what our posterior is proportional to. but we can't compute the denominator exactly because it involves this completely intractable sum, right? Like computing the denominator requires summing over every possible combination of the group labels. And there's no way we can do that. Like maybe we could do it if there's, I don't know, like 3 or 4 data points, but imagine you have 1,000 people. Doing a sum over 2 to the 1,000 possible combinations is a complete non-starter. And so this is why we need approximate inference. All right, so in this video, I'm going to talk about the big picture behind Markov chain Monte Carlo, and like explain why it even has that name. So remember with rejection sampling, what did we do? Well, we like generated a whole bunch of proposal samples, and then we basically said like some of them we're going to keep and some of them we're going to reject, right? So we generated a bunch and we randomly rejected some of them. So if you think about like in terms of, let's say you're playing darts, right? It's sort of like, well, I'm just going to like close my eyes and generate like a whole bunch of samples. And then I'm going to like look at which ones were kind of good and say like, let's keep the ones that are maybe like closer to the bullseye and throw the ones that are farther away. But like, if I'm going to get to throw 20 darts, right? Maybe it makes more sense to like, instead of just like blindly throwing them all like rejection sampling does, maybe it would make more sense to say, let me like throw the first dart, look at where it lands and then kind of adjust, right? Like, let's say I throw the first dart and I'm like way, way off, right? Like I throw it way over there, but the target is here. Then I say, oh, I need to move more this way. So that's the idea behind Markov chain Monte Carlo. It says, let's use the samples that we already have and maybe like modify them or adjust them to give us better samples. So to write things out mathematically, what we get is we have a set of samples. So we have theta 1, which is our first sample. And we use that to figure out a way to get theta 2, which is like our second sample. And here, like theta 1 is just like a way of saying these are like a particular set of values, right? Maybe theta is like the means of, my heights for 2 groups. And so like theta 1, the sample is like first group mean is like 5.9, second group mean is 5.4. Then I use that to like give me another sample. And theta 2 is like, another like a vector of mean. So this is each theta represents one sample from my distribution. If it's scalar, it's a single number. If theta is a vector or like a high dimensional thing, it's all of them. And so then I use theta 2 to give me theta 3. And I'm using this weird superscript notation because I want to save the subscripts for like, there's like, if there's 5 different thetas, I want to use 5 different like hidden variables. I want to use the subscript for that. Okay, and what we're going to do with Markov chain Monte Carlo is we're going to set it up so that when we change from theta 1 to theta 2, like the process that we use, this arrow, we're going to set it up so that those arrows become transitions in a Markov chain. And we're also going to set it up so that that Markov chain ends up being the steady state distribution. And if that sounds kind of like black magic, it should. This is weird. Like, how do you set it up so that you end up in the steady state distribution? And that's what we'll see how to do. And why is that important? It's because that means that if I do this process all for a long time, then eventually my theta is going to look like a sample from the true distribution, right? Because the Markov chain is going to converge to its stationary distribution, and we're going to set it up so that its stationary distribution is the true distribution of the samples. So the key in all MCMC methods is to choose the transitions wisely. Right, so we get to choose how we do that, and we'll talk about 2 different algorithms for doing that. In this video, we're going to talk about the Metropolis-Hastings algorithm for sampling from a distribution. Remember, we want some distribution, we can't compute it exactly, and so we're approximating using samples. But what we do have is an unnormalized version of that distribution. And so what I'm showing here is an unnormalized distribution. It has this kind of like weird funky shape. And I'm going to call it Q of theta. I'm calling it Q because it's not like a probability distribution. It's not a proper density. So I'm using letter Q instead of letter P. And this maybe might be like P of theta given X. It's like your posterior, the unnormalized version, what have you. And remember with Markov chain Monte Carlo, we're generating a series of samples, right? We have theta 0, which is like our first sample. And instead of just like generating a completely new proposal, like completely from scratch, we're going to say, well, let's use theta 0 and somehow use like this unnormalized version of the distribution to somehow get us to the next sample, and use that sample and q to somehow get to the next sample and so on. And so the way we're going to go from one sample to the other is pretty similar to rejection sampling. Is going to be a two-step process. The first step is we're going to generate a proposal, like a possibility for, well, if I'm at theta like 4, then what are the possible theta 5s I can pick? That's the first step. It's going to be a proposal step. The second step, so let me write that down. Well, first step will be a proposal step. And the second step will be, just like before, an accept reject decision. So we'll decide to accept that candidate proposal with some probability. And let's talk about how we actually do these proposals and how we decide whether or not to accept them. So the proposal will come from something we'll call a proposal distribution. And we're going to notationally write this out as v of theta prime given theta. And basically what this says is, given the previous sample, this is a distribution over the next sample. Right? So like if I'm at theta equals 3, then this is a distribution that says, okay, like maybe randomly pick something uniformly between, I don't know, like 2 and 4, or maybe have a normal distribution centered at 3 and draw a sample from there. So this proposal usually should be something that's pretty easy to generate samples from. It should be something that kind of, helps you move around and like generate samples well enough. We'll talk a little more about that later. But this is some distribution that we can draw samples from. This is like something that we can say, okay, here's like the next sample that you might get. Now we'll have to figure out whether or not we should accept or reject it. And to do that, let's actually think about, let's suppose that, I have some sample, and the sample I have is at this particular value of theta, right? Let's say this is my theta at sample number t, and I'm evaluating kind of two different proposals. One is this one I'm drawing dotted in red, right? This is, I'll use theta t plus 1 question mark. And the other is this one, right? Let's suppose that, two different possible things my proposal generated were the red and the green. So maybe we get this red dashed line or this green solid theta. We get one of them maybe. So which one should we like favor over the other? Well, it kind of seems like we want more samples in the area of the green one, right? Because that's where this density, this distribution has like a lot more weight. So we should be generating a lot more samples that look like the green one. And we kind of should be generating a lot fewer samples that look like the red one because it has lower probability. And it even has lower probability than like the theta t we originally started at, right? So we can kind of think of this as like medium, we can think of this as like low, and we can think of this as high, right? And so if we're going from medium to high, we should generally say, yeah, like I want more samples like that. But if we're going from medium to low, we should say, I don't really want as many samples like that. And so what we'll do is we'll set up our acceptance probability. Let's maybe move this so it's a little easier to read. Our acceptance probability will be then the ratio q of theta prime divided by q of theta. Okay, so this seems like a pretty reasonable thing to do, right? Like if q, the new sample has proposal, oops. Let's actually make this a little clearer. The new proposal we'll call, we'll write out explicitly, this is theta prime, will be drawn from the proposal distribution, and we'll accept it with probability q of theta prime divided by q of theta. Now, this seems reasonable, right? Like if q of theta prime is way bigger, then that's good. If q of theta prime is a lot smaller, then this probability will go down. But there's a problem, which is that if q of theta prime is bigger than q of theta, then we don't really want to be doing that, because then that's a probability that's greater than 1, right? So we have to just add a simple min. Let me actually make this a little easier to read. right? What we really want is we really want to say, well, okay, let's just take this ratio and let's like cap it off at 1. So we'll look at the min of 1 and this ratio. And you can see I've left some room because we're not quite done yet, right? What if my proposal distribution, like let's say that I'm looking at theta t and I'm comparing, like maybe I want to choose the green sample. But instead of choosing, I know I said maybe you're going to use a uniform. Let's suppose my proposal distribution is asymmetric. For whatever reason, let's suppose it's more likely to give me samples that are bigger than theta t than smaller, right? It's sort of like skews to the right. Well, in that case, then, or it's not skews to the right, it has more weight on values above theta t than below, right? In that case, I should think, well, my proposal distribution is kind of unfair and I need to somehow compensate for that, right? So I need to add in some term here that helps me compensate for the fact that my proposal distribution might be unfair, right? It might unfairly say, well, maybe, you know, the new theta prime was just like more likely under the proposal distribution. So maybe I can do something like I can divide by if the new theta prime was like way more likely than the old one, then I should like divide by that, right? Like I want to get it smaller. But this is not quite right because then like, well, what if it's symmetric, right? If it's symmetric, then we've just unnecessarily divided by something, right? So let's, in the numerator, put going the opposite way, right? So the numerator says, okay, like what's the probability of, what's the, you know, the probability of getting theta given that you were at theta prime? Like what's the probability of coming back from that sample? And the denominator says, what's the probability of going there? And if the probability of, you know, going there and coming back are the same, that thing cancels out to 1, which for most proposal distributions it does, but we need to include that just in case. And this is the Metropolis-Hastings algorithm. This is all there is to it. So what do? We start, so, you know, theta 0 you usually just pick randomly. And then you start by generating a proposal. You compute this ratio here, or this product. You say this is some probability, and you accept that new sample with this probability. And if you reject it, you just repeat. And if you accept it, you keep that sample. Great, that's the sample. And now you keep going. And that's the Metropolis-Hastings algorithm. The Metropolis-Hastings algorithm can be kind of sensitive to your choice of proposal. So for example, let's take this distribution here that we were just looking at. And let's suppose that this goes from values of theta from, I don't know, let's say 30 to 80, right? Let's suppose that that's our range of possible values. And let's think about different proposal distributions. Well, first off, it seems like we like symmetric proposals more than asymmetric proposals, though that may not work in every case. It also looks like, let's suppose let's try V of theta prime given theta. Let's suppose it's uniform from theta minus 500 to theta plus 500. Well, this doesn't seem great, right? Because what happens if we try this out? Well, let's say we start at this black point theta t, which I don't know, looks maybe like 45-ish to me. So we start there, and then we say, okay, let's like generate something uniformly between negative, what's like 45 minus 500, right? So negative like 450 to positive 545, right? So this is like a huge range. And most of those proposals are going to fall outside where the blue curve is actually 0. And what is that going to mean? That's going to mean that this ratio here, if your new theta prime falls outside where Q of theta prime is 0, then you're going to accept the probability 0. And you're going to end up rejecting most of your samples. So this one, not so good, right? Okay, like what if we say, okay, let's like try something a lot smaller. Let's say V of theta prime given theta is uniform. So, okay, too big is bad. So let's do theta minus 0.1 to theta plus 0.1, right? Like too big is bad, so let's try going a lot smaller. Well, now what's the problem? The problem here is that when we think about theta t, then theta t plus 1 is going to be really, really, really close, right? Like, again, if we're at 45, then we're not going to get values far beyond, like, well, we're not going to get any values beyond 44.9 and 45.1. That means it's going to take a long time. We're going to have to generate a lot of samples before we explore the entirety of this distribution. And that's bad because, ideally we want to just like generate a bunch of samples and not have too long before, they show us the entire shape of the distribution. So choosing your proposal distribution too narrow is bad. Choosing it too wide is bad. And so there's kind of an art to choosing it somewhere in between. Notice that unlike rejection sampling, we don't have any constraints like, oh, it has to like be strictly above the distribution. This is much more of an art. It's much more of thinking about, well, like what are reasonable values that I might want to see, that I might not want to see, and so on. Let's think about one more example with Metropolis Hastings. And let's suppose that we have a distribution that looks like this, right? Now we need to choose a proposal distribution that's wide enough, right? When doing Metropolis Hastings, we need to choose something that's wide enough to be able to get between these two regions of the distribution, right? Like looking at this, we really have like, there's like the low part and then there's like the high part, right? And we need to have, if we're going to do approximate this at sampling, we need a proposal distribution that will like, let's say we start out over here on the left side, we need something that's going to like generate proposals that are big enough to send us over here, right? So we need proposals that are, relatively large. But if our proposals are relatively large like that, then, they may, if we're already here and there's a decent probability of going that far to the right, then we might end up just all the way generating a bunch of proposals all the way over here. So the shape of this distribution is not really that great for doing something like this, right? This is kind of a tricky distribution. And we'll talk a little bit more about why distributions like this are tricky and what kind of challenges they present when we talk about the relationship between Metropolis Hastings, MCMC, and mixing time. Now we're going to talk about Gibbs sampling. And Gibbs sampling is a kind of variant on Metropolis Hastings. The pros are that it's very easy to describe. It's very intuitive. It makes a lot of sense. One of the cons is that it only really makes sense. It's only really kind of valuable when thinking about problems involving multiple hidden variables, right? So it's not just like a single theta like we've been looking at for some of our examples. It's like, you have some theta 1 and some theta 2. And in our Gaussian mixture model example, that's like, well, we have the mean of the first group and the mean of the second group and the hidden labels, the group memberships, right? And in most real world cases, you have multiple hidden variables. And so Gibbs sampling ends up being very useful. So how does it work? Well, it's quite simple. We say, let's suppose we have theta, which is really like, theta 1, theta 2, and so on up to, I don't know, we'll call it theta k. And what we want is we want a bunch of samples, right? We want theta 0, theta 1, theta 2, and we've already talked about why we want these samples. But what we really want is, we want to find some way to really easily get from one sample to the next, right? That's this whole idea behind Markov chain Monte Carlo, is finding ways it's really easy to get from one sample to the next. And remember when I say theta 2 like this really means, theta 2 is really equal to the first hidden variable for the second iteration, the second hidden variable for the second iteration, the third hidden variable for that iteration, and so on. Right, so each one of these is really a vector, right? It's sort of like all the different hidden variables in your model. Now, Gibbs sampling is really useful when the joint distribution, right? So P of theta 1, theta 2, and so on, theta k, given your data, is hard to compute. But it's really useful when, sure, maybe the full joint distribution is hard to compute because like you got all these different things going on. But let's suppose that if I just look at one, right? If I say, okay, let's suppose that like instead of trying to figure out all of them together, let's suppose like maybe hypothetically I knew theta 2 through theta k, right? Like I knew theta 2, I knew theta 3, then would it be easier to figure out what theta 1 is in that case? In other words, can I figure out the conditional distribution theta 1 given theta 2, theta 3, and so on, and the data, right? Instead of figuring out like the joint posterior over all my hidden variables, let's say I'm just going to fix a bunch of them and look at the distribution of the remaining one. So in cases where this is easy, and in a lot of models, we'll actually end up setting things up so that this does become easy, and you'll see an example of this in discussion, then this works out really well, right? So let's suppose we can actually draw samples from this. Maybe it turns out that the joint distribution here is like hard and complicated and involves computing some intractable sum, but maybe it turns out that this distribution here is, this one here, is really just like, maybe it just happens to be a normal distribution, or maybe it just happens to be an exponential. And we'll see there are lots of models that are actually set up so that it ends up being that way, right? Where theta 1, if I knew all the others, has some really simple distribution. And similarly for theta 2, right? We have to be able to compute theta 2 given theta 1, theta 3, and so on, and so on and so forth. And so the idea here is very straightforward, right? We just start by having some theta 0, and then theta 1 to get, so we start with some first theta sample theta 0. And to get our next sample theta 1, all we're going to do is we're going to pick one of the variables, one of the hidden variables, and resample it out of the corresponding conditional distribution. So we'll start, so step 1 is initialize theta 0, right? However you want. Step 2 is resample theta 1 based on theta 2 and so on. And then that new vector with your new theta 1 and your old theta 2, your old theta 3, and so on, that's your new, this is your new sample, right? Next, you're going to resample theta 2. Theta 2, and we'll resample that and drop that in, right? So that's theta 1 that we just got. Then there's like theta 2, which is new, and there's all the other ones from before. And we're just going to keep repeating this process over and over and over, right? So we'll do theta 1, theta 2, all the way up to theta k, and then we'll just start right back over at theta 1, right? Sometimes you'll see people kind of like randomize the order, switch things up. You'll see variants like that. But the core idea is fix almost all of your variables and then resample a few others given those, and then repeat over and over and over and over. And that's Gibbs sampling. It works great when you can compute these conditional distributions, these sort of like partial conditional posteriors, a lot more easily than you can compute the full posterior, which I've highlighted in yellow. And it tends to be widely used in practice for that reason. Let's think about the performance, the efficiency of Gibbs sampling. So if we think about this process, then what we're doing is we're really saying, okay, let's like keep sampling theta 1, then we sample theta 2. And so if there's a lot of hidden variables, then we have to repeat this process a lot of times, right? Let's say that there's 1,000, like, you know, it goes, k is like 1,000. So we have theta 1 all the way up to 1,000. Then we have to do 1,000 different samples before we've kind of like refreshed all of the variables. So there's some variants that people use. Sometimes people will do what's called block Gibbs sampling. So there's block sampling, Gibbs sampling, where we, instead of one at a time, we do a group at a time, right? Maybe, and this only works in cases where this is easy. Maybe instead of like computing theta 1, given all of these, maybe it's easy to do like theta 1, theta 2, and theta 4, given theta 3, theta 5, 6, all the way through k, right? And then maybe the next time around, it's easy to do like 3, 7, and 10. And then the next time it's easy to do 4, 6. Maybe it turns out that, you know, 1, 2, and 4 have a multivariate normal. So this really depends on the structure of your model. anytime you can get away with this, you should, because it's a lot more efficient, right? You're changing more things at once. You're kind of like resampling and like refreshing your samples more. That tends to be better. Another thing people do is something called collapsed Gibbs sampling. This tends to be computationally a lot more challenging. It tends to like require you to like think a lot more about your model and like really have a deep mathematical understanding of what's going on for more complex models. But we say, well, sometimes can we marginalize over some hidden variables, right? Maybe you set up your model so that you don't actually care about all of the thetas. Maybe you don't care about theta 7 and theta 10 and theta 13. And maybe you don't care about like thetas 20 through 500 either. But you've put them in your model because it makes it a lot more convenient to write everything else out. So in cases like that, you can actually people do what's called collapsed Gibbs sampling, where they marginalize out over those variables that you're not interested in. And then that tends to give you better samples from the remaining variables. So these are kind of some variants. We're not expecting that you necessarily fully understand how they work, but more to give you a flavor of like, how can you take these algorithms and adapt them? What kind of changes can you make to them? Let's do a little demo to kind of illustrate how Gibbs sampling works and kind of like build some intuition for it. So let's suppose we have this really simple distribution where our distribution is uniform over the unit circle, right? So we have two variables, they're x1 and x2, right? One shown on the x-axis, one shown on the y-axis. And we want to generate samples from this distribution. And this is kind of like a silly example because we know exactly what it is. We also saw how we could use rejection sampling to generate samples as well. But let's try using Gibbs sampling to get us samples from this. So we have, this distribution we have over the unit circle uniform. And I, initialize my first sample randomly at this red point. Now, what we do is we say, okay, let's fix one of the variables. So let's fix x2, the thing on the y-axis, and let's look at x1. Well, given x2, then x1 is uniform on this black line, right? If both of them are like uniform over the whole circle, then like condition on a particular value of x2, then x1 is uniform over this black line. Now, next, we're just going to draw a particular value. You can see I got unlucky with this choice because it's really close to the previous one, but that's my random draw. And now that's my next sample. Now, great. Okay, so that's my next sample. What do I do? Now I fix x1 and say, how do I generate a new value of x2 given that value of x1? Well, again, x2 is uniform from here to here. So I generate a sample. Great, I got that one. Now I repeat again. I fix x2 and I get a new value of x1, which is there. And then I look, okay, let me like resample a new value for x2. It was there. Again, I'm getting unlucky with these things that are really close, but I repeat and then I get that one. Then I fix this and I sample from this vertical line. I get one there. Then I fix this. I sample from this horizontal line. I get that one, and so on and so on, right? So I keep repeating this process where each time I kind of like anchor, one variable and like sample the other. And then I alternate, I anchor the other variable and I sample this one. And if I repeat this process over and over, then eventually I'll get a whole bunch of samples from the true distribution. So let's walk through how would we actually implement this in code. Well, I have some skeleton code here that does a lot of it for you. So we have, how many iterations we're going to do. I, made up this initial sample kind of randomly. And what we're going to do is we're going to do a loop. And what we're going to do is we're going to fill in these key parts of the loop where we sample x1 given x2. And similarly, we sample x2 given x1. So how do we actually do the sample? Well, we saw graphically that it was kind of like uniform on this horizontal or vertical line. So if we know what the value of x2 is, that's like the thing on the y-axis, then we're kind of like fixing the y and we're looking for the horizontal value. And so if I go over here, I can see, well, over here, I'm fixing this particular value of x1, right? Like maybe it's, I don't know, like 0.3-ish. And so what is the range of possible values, or sorry, x1 is like 0.2-ish, right? It's this on this vertical line. I'm fixing this and I'm saying, what are the possible values of x2? Well, it's from here to here. How do I compute this? Well, I can use the Pythagorean theorem. I know the circle is centered at 0, 0. And I know this side of it is 1 because it's the unit circle. And I know this leg of the triangle. And so I just need to know this leg, and then I can sort of just like double it to get to each side. Right? So I can do a little bit of geometry. So this is really, by Pythagorean theorem, it's the square root of the hypotenuse, which is 1 minus x2. And that's not the value of x1, right? That's sort of like the maximum possible value. That's the top of the circle. So we'll call this x1 max. And then the lowest possible value is like just the negative of that, right? We just kind of flip. So negative x1 max. And now x1, we just draw a uniform random variable from there. So this is uniform from x1 min to x1 max. And similarly for x2, we repeat a very, very similar process, right? We say the maximum possible value, again, using a little Pythagorean theorem and some geometry. It's 1 squared, which is 1 minus x1. 1 squared is 1, but I'm leaving this in the code so like it's a little easier to see that this is a Pythagorean theorem computation. Now, and then x2 min equals negative x2 max. And x2 is also a uniform draw from x2 min to x2 max. All right, and so now and then what happens is each time I'm appending the samples. Here I'm keeping all the samples. You know, in practice, if I were doing this in the real world, I'd like throw a bunch of them away at the beginning and only keep one every so many iterations. But we can see here that already the samples look pretty good. This is a case where the mixing time of this Markov chain is relatively fast, because you can see that if I change, as long as you're like kind of near the middle of the circle and not like way out at the edge, and even if you are way out at the edge, you know, by the time you've run a few iterations, by the time you've run one iteration, you've changed one variable almost completely, you know, to unlike what it was before. And by the time you run another iteration, you've changed the other one almost completely to what it was before. So the mixing time of this particular distribution is relatively fast, which kind of sort of justifies me keeping all the samples. Okay, that's an example of doing Gibbs sampling. We've talked about a few different ways of doing this thing called Markov chain Monte Carlo, where like we generate a sequence of samples where each one kind of depends on the previous one. But what I want at the end of the day is I want samples from my posterior distribution P of theta given X, right? And what I want to know is, are these like samples I generated in this process? Are they actually samples from P of theta given X, or are they just like these things that kind of like heuristically seem reasonable? So I really want to know how I can relate the samples I got using the procedures we just learned to actual things about the true posterior distribution, right? So, because remember, in order to generate these samples, we use this unnormalized version of what we were looking for, which is like this distribution Q of theta, right? Which is not actually like a density. It doesn't integrate to 1. We don't know what the constant is, but it sort of was good enough to like help us get samples. So what is the relationship between these samples and the true posterior? Well, this is where the theory of MCMC helps us connect the two. So let's think about this sequence of samples, right? To get from like theta 2 to theta 3, it's random, right? Like we're randomly changing some stuff. And each sample only depends on the one before it and only affects the one after it. So that means that the series of samples form a Markov chain, right? So this sequence here forms a Markov chain. All right, so that's an interesting fact. And why is it useful? It's useful because it turns out that with Metropolis Hastings or Gibbs sampling, that the stationary distribution of this Markov chain, so theory tells us that the stationary distribution of this chain is the actual distribution that we're interested in sampling from. So if we use Q of theta to generate in Metropolis Hastings, or if we use this series of like conditional probabilities of like one variable at a time in Gibbs sampling, then it turns out that that process really gives us the stationary distribution as the actual P of theta given X. Okay, so why is that useful? Well, that means that if we take, theta 0, initialize it to wherever, right? Like remember, if you start off anywhere in a Markov chain, you start off in some state and you run it for a whole bunch of iterations, then you look at where you end up many, many iterations later, you're going to end up in the stationary distribution, right? So if you run the chain for many iterations and you look at what you got, what you'll get is actually a sample from the true posterior. So does that mean that we actually can't use like all of the samples? We have to like just use one from after running it many, many times? Well, the answer is kind of yes and kind of no, right? If you wanted to be like completely theoretically guaranteed, then yeah, you would like maybe try to compute theoretically what is the mixing time of your Markov chain based on your distribution and your algorithm. In practice, what people do is people say, we'll initialize theta 0 somewhere, and we'll, run the chain for a whole bunch of iterations. And then maybe around, I don't know, like say 500 or so, we'll say, okay, we'll just like throw away the first, 499, and we'll think like maybe 500 seems like a reasonable guess for the mixing time. So I'll take the 500 sample. That's one sample. Great. Now to get the next sample, do I start, initialize randomly and start all over again? Well, no, right? Because like this sample, like somehow the sample number 500 is like maybe more random-ish intuitively than sample 0, right? Because like I chose sample 0, like, I could have done a bad job of choosing it. So maybe if I start from 500, maybe I don't have to run it for nearly as many steps, right? And so what people do is they'll say, okay, well, like let's just run it for 100 steps. And that's my sample, right? And that's my next sample. So what we have now after running the chain for 600 iterations is 2 samples from the true posterior, approximately. And we keep running this, many times. Note that this computationally is very easy to parallelize, right? Like I have one chain that I've drawn here. You can imagine running like if you have multiple cores on your machine, you can run multiple chains in parallel. And most software packages that do this actually will run at least 4 chains, if not more. If you have a big cluster, you can run a lot more, and so on. Now, why did we talk about mixing time so much last time? Well, the reason we talked about mixing time is because whether or not these samples look like actual samples from the stationary distribution, right? Like, do we actually get to the stationary distribution in 500 samples? Well, it depends on the mixing time of the Markov chain, right? If your Markov chain has a structure where it's really hard to move around between states, then your mixing time is going to be pretty long, and you're probably not going to get to the stationary distribution in 500 iterations, right? If you're constantly rejecting samples, it's also going to take you a long time to get to 500 iterations. So the ideas we've talked about with like choosing a good proposal distribution, doing like block Gibbs sampling, those are ways of making your Markov chain mix faster. In other words, those are ways of moving faster in the kind of like space of all possible thetas. You're moving around in that space a lot faster. And so your Markov chain is going to mix faster, and you're going to end up in the true distribution a lot faster. And there are variants on Metropolis Hastings that actually like take advantage of the structure and kind of like really think about how do you make the mixing time as small as possible. There are things like called the Hamiltonian Monte Carlo, and this is actually what PyMC3 uses, that really are focused on exploiting this idea of mixing time. And so again, we're not necessarily expecting you to like doing computations with the mixing time, but really have an intuitive understanding, right? Like if you think about the distribution we looked at earlier that looked like this, in a distribution like this, your mixing time is probably going to be really slow because you have 2 modes of the distribution, and it's really hard to get from one to the other, right? If you have a sample in here, it's going to take you a long time to get to here, right? And similarly, you can imagine in high dimensions, if your distribution has like a lot of these little pockets and it's really hard to move around between them, then that means your mixing time is going to be slower. So I want to now recap what we've learned with sampling and approximate inference. So remember, we started off with this idea, we have some distribution we want to compute, but we can't compute it exactly. Usually it's like the posterior distribution of our parameters given our data, and we can't compute it exactly. So what we do instead is we compute this unnormalized version, right? Because there's this like term in the denominator that we can't compute. And so we can compute the numerator just fine. And so we use that to do approximate inference with sampling. And how do we do that with sampling? Well, we say, okay, instead of actually giving you the true posterior distribution, instead I say, well, let me look at like samples from that distribution. Let me look at a bunch of samples and use those to approximate the distribution. Now, just straight up sampling from the distribution, that's just as hard as computing it. So we're playing a bunch of tricks like rejection sampling and the two MCMC methods we learned to get around that and give us samples in a more clever way. Rejection sampling was this idea of, well, let's think about some proposal distribution, like a simple like uniform or normal. And we want to use that proposal distribution to give us samples. And for each of those samples that come out of the proposal, we say, maybe I'll accept this one, maybe I'll reject that one. And the probability was controlled by like how far apart the proposal and the actual thing I'm interested in are. Now that's rejection sampling, but it's kind of silly because like we end up rejecting a lot of samples, especially in high dimensions. So we didn't really, it's like an interesting idea. It gives us this idea and kind of practice working with like approximating distribution samples. It's really easy. It works in almost any case. It just tends to reject a lot of samples and therefore be kind of slow to give you enough samples to do something. Now, we also talked about Markov chain Monte Carlo, which was this idea of, well, let's like construct a Markov chain of samples where instead of just like giving you a fresh sample every time and making an accept reject decision, we like construct a chain of samples where we like build each sample on top of the previous one. And we construct that sequence of samples so that in the end, what we get is the stationary distribution of that Markov chain, that like one sample to the next, the next, the next, is the true distribution that we're interested in. And if that sounds kind of like, wait, like that's witchcraft, how did you do that? That's good because it is kind of magic, right? It is magical that we can take this, construct this chain of samples using what seemed like pretty intuitive ways of doing things. And the stationary distribution of that chain of samples was actually the true posterior distribution. So this is kind of a really, really cool fact that falls out. And there's a lot of interesting theory behind it as well, that if we do this sampling process a whole bunch of times and like go from one to the next, then eventually we'll end up in the steady state distribution, which is the true posterior distribution. Now, how did we actually construct that chain? Well, first we talked about Metropolis Hastings, which says, okay, like the first chain, like to get from one to the next, I have a proposal distribution. Now proposals are not like proposals to generate fresh samples. They're proposals on how do I tweak my existing sample to get a slightly different one. And, we looked at, well, if you like move around and you construct this ratio of like, the unnormalized probability at the new location divided by the old location, and you also include like how asymmetric your proposal is, then you can construct this process where you keep moving around and you end up with good samples. Now, that's Metropolis Hastings. There's also Gibbs sampling, which is, well, instead of like having a proposal distribution where you're always like, trying to like move around in some way, it's what if my proposal is just like I change one variable, right? Like what if I have multiple variables, which in most real world settings is the case, and I change one at a time from the distribution of that one conditioned on all the others, right? So I fix most of them. I look at one and I draw a new sample for just that one conditioned on the others. Then I repeat for the next one. I drew a new sample for that one conditioned on all the others. The next one, I draw a sample for that one conditioned on all the others. And I repeat this over and over and over, and that gives me samples. So these are a few different ways of doing it. And then we also talked about practical considerations, which are, well, sure, like the theory says, if you run this for long enough, it'll converge to the true stationary distribution, which is the true posterior. But what does long enough actually mean? And we talked about in practice, people just like run the chain for like a while, maybe like a few hundred iterations, and then they take that sample, and then they run it for like maybe, a little while, but not quite as long, take that sample, run it for like a little while, take that sample, and so on and so forth. And we talked about how the complexity of the distribution and like the cleverness of your algorithm, like how you choose the proposal, how many variables you like sample at the same time, affects the mixing time of your chain and affects the quality of your samples. So these are ways of doing Bayesian inference. These are ways of kind of setting things up so that you can actually infer and reason about the hidden variables in your model. And these are widely used in practice, as you saw on the lab, and as you'll see if you end up using these methods in the future.